Hi listeners, I'm Murthy, Associate Professor in the CST Department at Marri Laxman Reddy Institute of Technology and Management. In continuation with the previous topic of introduction to the data structures, now we'll deeply explore singly linked list, a fundamental data structures in the computer science. Okay. Unlike the static arrays, the singly linked list offers dynamic flexibility crucial for many applications because we can't predefine the required amount of memory in advance, or we can't utilize unnecessary or unused memory in the runtime. For in such cases, singly linked lists are very suitable data structures for its dynamic flexibility in implementation of any data. So in the singly linked list, data structure elements are connected through pointers. Okay, that means each and every data item, instead of consecutive memory locations, it is connected by links. Links means pointers from previous data item to the next data items. So every node, the data is organized in terms of the nodes. Every node contains data and a pointer or links to that stores the address of the next node. Through pointers, we can move from one data items to the next data items, next data items to the next data items, so that we can reach the end of the number of elements whatever we are going to maintain as part of the singly linked list. In any data requirements, in the database requirements or any other requirements, right? So the first data item is represented by a special pointer called as header. So this head contains the address of the first node. The first node contains address of the second node. Second node contains address of the third node, henceforth. But only thing is, in the last node, it contains null pointer to indicates end of the list, so that the traveling in the linked list can be terminated. So, for example, we are having the three data items 10, 20, 30. The head is representing address of the data item 10, and the node 10 contains not only the data element but also address of the data element 20 using this link. So, finally, the last node 30 contains data plus a null value to represent termination conditions. So, unlike arrays, linked lists are dynamic, no fixed size, allowing efficient insertions and deletion operations whenever necessary as per the requirement of the applications. So, traversal, in what way we can traversal in the linked list? That means in what way we can move from one element to the other element. In arrays, the traversal or moving to the specific location of the data element is using the index, so that we can directly calculate, identify the index. Using the index, we can directly move to the required locations. But in the linked list, the traversal is based on the link addresses, how it is efficiently it is containing in each and every node. So the traversal means visiting each node in the linked list exactly once, from first node to last node, in order to insert any element, or in order to delete any element, or in order to find any element, or simply say in order to process any data elements in the linked list. So, but only thing is, all these elements must be traverse or identified in a sequential order only. Always begin from the starting or first node by representation of the header or head simply in the list. So, moving from a head, automatically we are identifying the first node. From first node, we can move from the current node to the next node by using the pointer until a null pointer is encountered. So, in what way we are traversing in the linked list? Using the head, we can identify the first node. From the first node, that or the current node, we can reach to the next node in the sequential order using the pointer variable. So the pointer variable is containing the address of the next available data item, next available of the node. Okay, so signaling the end of the list whenever we reach null pointer. So what is the time complexity? How much time we take in traversing number of elements in the linked list, or to cover all elements exactly once from first element to the last element? That only thing is, unlike in the array, as we can reach to the any elements either in the first element or middle element or last element directly calculated from the index. But here, as we need to move from first element to last element by sequentially moving from first element to second, second to third, henceforth to the last element, it takes O of n time. That means time complexity of reaching the last node, or in average case of identifying any particular node in the linked list, is O of n. What is the meaning of this O of n? Means in order to identify any node in the linked list, we required, on an average case or worst case, we required O of n time. It has to process n number of elements. That means we are starting from the head. From the head, we can reach the first element. From the first element, through this link, we are reaching the second element. From the second element, we are reaching the third element. From the third, we are reaching the fourth element. From that element, we are reaching the last element. Only thing is, at the last element, we are having the null pointer was stored. This null pointer is indicating the end of the node. Wherever we reach this null, it indicates the last pointer. Until and this particular thing, every node contains a pointer variable indicates next element. This is the traversal from first node to the last node, or the required element in the given linked list. So for example, in the previous case, all those nodes, that means data elements, the 7, 11, 3, 2, 9 organized in the manner of a nodes. The first node indicates 7, second node indicates 11, third node indicates 3, fourth node indicates 2, and the next node is indicating the 9. Okay, so to visit the last node, we required these are the number of sequential accesses. So we now will see it is the process of identifying or moving from one node to other node in the linked list. We now will identify in what way we can insert any particular elements in the linked list. In the array, using index, we can reach to any location directly and we can store. But in the linked list, we are having to insert element in a systematic way. We are having the three different types of insertion operations. The element can be inserted at the beginning of the linked list, or we can insert nodes at the end of the linked list, and we can insert any element at any specific location in the linked list. So why we require these three different types of requirements is based on the application requirements, application implementations. Some elements are required most suitable to be inserted at the beginning. Some elements most frequently we are inserting at the end to represent the application, or else as per the requirement we can insert at any particular location. See, whenever we are inserting any particular element, the new node to be inserted at the beginning, what it indicates is we simply need to create a new node. We are already having a fixed set of nodes. Say for example, A, B, C, D are already available nodes in the linked list. We want to create a new node called as E, but we want to make this E as first node. So previously this head pointer is representing first node A. Now if you want to make E as the first node, automatically A becomes second node. So the head has to represent this E. After E, we are using the next address. we need to represent A, so that from head we can directly reach the E as the first node. From E we can reach the second node, that means the previous first node as now second node. Then after A we can follow the sequence, that means A to B, B to C, C to D. Finally, whenever we are reaching the null, we can stop. Right? This is the way we can insert a particular node at the beginning, or else sometimes based on the application requirements, we may need to add a new node, say the same E after D. So what happens? Previously, through the special pointer head, we are reaching the A. From A, we reaches B. From B, we reaches C. From C, we reaches the previous last node D. Now, if you insert E as last node, the previous last node becomes last but one node. So, simply what we need to do is the address of E must be copied in the D's next link. What it means, in the previous D contains null value to indicate the last node. The last node address is replaced with this new last node E address. Now, once this link is established, D becomes last but one, E becomes the last node. But only thing is, in order to identify E as the last node, the address in the next field of the E must be set as null value. So once we did this particular thing, irrespective of the number of elements before D, automatically D is going to previous last node D is going to becomes last but one, E is going to becomes last node of the linked list. Or else, whenever you want to insert any particular node in the middle or in a particular specific location, in the way we need, only thing is we need to identify where we need to insert this particular node, after a particular node or before a particular node, or based on the number of locations. Only thing is we need to start from here, we need to traverse till the previously identified nodes, either before node or last node, that location. Once we found, say for example, we want to insert this new E between B and C. So only thing is we need to identify either B or C. Based on it, we can adjust links. So for example, simplicity, we can identify the B node. Once B node is identified, while moving from first node to B, that means using a temporary variable. The temporary variable may represents the A's next is equal to B, B's next is equal to C, like that. Whatever the required node, we can identify. Once you identify the required node, in that required node's next value, we can copy address of E. The previous B's next node, we can copy in the newly inserted E node, because this address previously is available in B. Now that value is copied in E, and this value's address is copied in the B value, so that we can automatically, this new node is now inserted between B and C. Similarly, we can insert this particular values in any order. So after this insertion, if you are inserting at the begin, previously if the list of nodes are A, B, C, D, now it becomes EA, B, C, D, or if you are inserting at the end, the list of nodes becomes A, B, C, D, E. If you are inserting in the middle, it becomes A, B, E, C, D. So in such fashion, we can insert any node at any specific position. Similarly, whenever a node is processed or it's completed its operation, whenever you want to remove that particular thing from the list, we can remove the particular node from the linked list at three different places. One is, it can be deleted the first node, or we can delete at the last node, or we can delete in the middle of the node. Okay, so in what way we can remove the particular element in the first node means, The thing is, the first previous head contains the address of the A, that means previous first node. A contains the next node, that means second node B. Only thing is, we need to replace whatever the address A which was contained in the head with address of B. So head previously contained address of the first node. Now we are replacing the head with address of the second node. This simple modification will remove the first node logically from the linked list. Later we can free up this address. Similarly, whenever you want to delete last node, so last node, if you want to delete the last node, what is the requirement? So if you are deleted last node logically, last but one node is going to becomes the new last node. So here we required the last but one node in order to remove the last node. Whenever you want to remove this particular last node, so we need to start with the head. We need to traverse from first node to second node to third node to the next nodes, until we are going to identify two nodes logically. The node contain null value, whatever the node that contains address of the last node. So if you are whenever we are moving from first node to the last node can be identified with the node which is containing the null value, that is the last node. Last but one node is nothing but the node which contain address of the last node. So once you are identifying these two nodes, simply last but one node's address will be replaced with null, as previously it contains last node address. Now the last but one node's address is replaced with null. It logically disconnects last node with the given linked list. Later we can free up the whatever the memory which was occupied by last node. This is the way we are restricting the linked list from first node to last but one node. Similarly, the deletions can also be performed at any particular location or particular based on the particular value. So based on the particular location or particular value, once again we need to start uh, traverse from header node to move first node or to the required node. Say for example, this 6 is going to be the required node. So once you the thing, we need to identify the required node, like previously as we identified last node plus last but one node. Here also we are going to identify the required node with contains the value or the location and its previous node. So once we identify these two nodes by just moving from particular node to next node by using node is equal to node next, we can identify the previous node and the required node. Once identified these particular nodes, the previous node address it should be replaced by the required node whatever it contains the address. Once this address is replaced by whatever the address containing in the deleted node, this address copies here. So it logically eliminates the node to be deleted. So in such fashion, we can delete any node at a specific position or any required node if available in the linked list. So this is the say for example, previously we are having the 3, 6, 12, 15 in this above condition, where if whenever you are deleting the node 6, automatically the list contains 3, 12, 15. Only the 6 node will be logically deleted. So what process we did in the previously? So whenever we want to set any particular element in the given list, we are starting from header node. That means whatever the node address which is available in head variable. So that is the first node. In the first node, we start comparing the data, whether the whatever the data contained in the particular node is the required value or not. Okay, if the value is matching in the first node itself, say we can declare the node is available, we can perform any other required operation. If the data is not matched with whatever the node that is represented by the header, then we need to move to the next node using the next pointer. That means logically we are moving from first node to next node. Once again, we compare the data. If the data is matched, we can declare the required data is available. Otherwise, once again, we process or we continue to move to the next node. Okay, but this comparing the data, moving to the next node will be continued till we are either we are getting the required value or you are reaching the last node. The condition which are required, which are identified as we already reached the last node is if the any particular node the next pointer variable is null, it indicates you already reached the last node, there is no more node after this particular node, so that we can stop. Okay, so till that particular time, if your matching is there, we are already declaring the data is available. Even we are reaching the null pointer and there is no match found, then declare the required item is not available in the linked list. What is the time complexity that generally whenever we are traversing in the linked list is O of n, because we can't predict where the data is available. We can't directly jump into the particular location or directly identify the value. The only way in the linked list to identify a specific element is start from head, compare sequentially node by node, and move to the next node using the next pointer variable. So you have to sequentially process first element to the last element. So all n elements must be processed sequentially. Hence, the time complexity is O of n. So where we can use this linked list, that is the main thing, because we are having when compared to the arrays element can be directly processed, directly we can reach, but wherever dynamic memory allocation is required, because arrays are static memory allocation, whether you need or not, whether you are using or not, you have to create an array with maximum number of locations. If the maximum number of locations are too high, memory usage will be very less and remaining all locations are waste. If you are creating an array with very few elements, if you require more number of locations, more number of data items, we can't add any more data, not even the single element to the existing array. You have to drop the array and once again you have to create new array. Once again you have to start entering the data from the beginning. But in the dynamic memory allocation, you can acquire any data element as and when required. We can start with 0. There is no upper limit. If the application demands, we can attach any number of memory locations. Only thing is one by one. Okay. So whenever dynamic memory allocation is crucial, okay, in particularly in the operating systems, okay, or whenever you want to identify or process memory blocks efficiently, we can use linked list. Okay, so similarly these linked lists are very crucial and very useful to create stacks and queues applications. Okay, the stacks and queues are always grows and shakes as per the application. So this dynamic sizing makes them ideal for abstract data types. So whenever you want to implement stacks and queues, linked lists are one of the better option to identify where to insert, where to delete. Similarly, we can add logically any number of data items. Similarly, these applications, thus linked list can be used. Various operations like undo operations, redo operations in the linked list is whenever it is the these are such operations are required, we can use uh, linked list as auxiliary data structures. Okay, each action can be a node. That each action means each undo operation, each redo operation, whatever we are performing, or any editor can be made as a node, allowing easy navigation through these changes in a systematic way. Similarly, these linked lists are very useful whenever you want to deal with polynomials. In the mathematics, the terms of polynomials can store are represented by nodes. Any polynomial can be effectively represented using the polynomials, and we can perform various applications, various operations on the polynomials using the linked list. Similarly, the uh, applications like musical playlists, image slideshows can easily implement linked lists. In particularly, if you want to repeat one more time or number of times, even you can use circular linked list is the perfect implementation requirement or method for continuous loops. Thank you.